Hello, everyone. So I will talk about Falcon, a new reliable transport over Lossy fabrics. Let's see if it works. Quick introduction of myself. My name is Yadong Li. I'm a senior principal engineer in Tom's organization, leading software architecture for 3 generations of IPU products at Intel. I have worked on IPU pretty much since the concept of the product to today, so it's a long time. Over the last few years, I have also leading 2 key technologies. One is for storage, this is NVMe over fabrics, fabrics offload in IPU. The second one, which is what we're talking about today, the reliable transport. So let's get into some details. So we have a simplified diagram here to illustrate the architecture for this reliable transport. Falcon as a hardware transport sits under RDMA protocol engine, and this block device interface, NVMe interface. So this is one reliable transport designed for all different usage models, right? For all the demanding workloads, including machine learning, AI, HPC, cloud RDMA, and the traditional RPCs and the storage networking. So it provides a reliable and a low latency hardware transport for RDMA messages and NVMe commands in cloud scale networking. So one of the key design principles behind this transport is to ensure full backward capability with the IB verbs-based RDMA applications. This is one very critical aspect of this transport. You don't need to make any change in the applications in the guest VMs to make use of this transport, right? So this is a very critical consideration from the cloud deployment environments point of view. It is a hardware transport, so it delivers a super low latency and high bandwidth for the applications, right? Including applications runs on top of this RDMA interface, and also the storage applications running on top of this NVMe. Both are standard interfaces, so that's very also critical for backward capability with the applications today. So one thing we also want to note here is, in addition to RDMA over Falcon hardware path, we built this NVMe over Falcon hardware path as well. So this includes actually for storage, it always includes both, right? Initiator side and the hardware target side. So we have a hardware path for both initiator use case and target use case. So this can provide a true end-to-end hardware path for storage disaggregation. It's a super low latency, low jitters. So you can find this very interesting in many other high performance or machine learning AI applications make use of this hardware path. So at the bottom of this picture, that shows, okay, from networking fabric point of view, Thomas already mentioned about this. There's no need to make use of this priority flow control. So this highly simplifies the switch management. This makes it easier for networking management and switch configurations. So Falcon transport, as a transport, it is a connection-oriented architecture, right? So it's designed with security in mind. So every connection has a security and authentication built in. We use this new security protocol, PSP. PSP make use of a lot of IPsec concepts, but it addressed the fundamental issues with the standard IPsec in cloud environments. So one is it makes it more scalable, removes, for example, security association on the receiver path. Second, the PSP protocol is flexible. You can leave a portion of in the L4 header in clear text, which is also very critical for networking management, because you can see in the TCP, UDP port number, or for this reliable transport, you can see some information like a connection ID and some other information. So it enables you to do all the interesting load balancing algorithms and also traffic monitoring and telemetry information. So this is super critical for cloud and for networking management. The standard IPsec causes a lot of headaches because it increases in the L4 headers. So that's one reason PSP is chosen for this architecture. It is hardware transport, so it delivers a consistent performance very low jitters in cloud scale, which we will show some performance data later. It comes with this state-of-art congestion control algorithm. Google is building a lot of algorithms based on the Swift, which uses time steps, time delay. Intel basically implement a similar algorithm and with Swift as the baseline with multipath load balancing algorithm as well. From an architecture point of view, we support this programmable congestion control, which I will talk about in the next few minutes. Is another very critical design principle to enable flexibility, enable top CSPs to keep doing the innovations in the congestion control algorithm. The transport design implements select ACK, retry per path. So the hardware, the NIC can do the multipath load balancing algorithm as well, which can really make that load balancing packet spoiling more efficient in different use cases. The architecture supports in-ordered connections and unordered connections. This is also one very different aspect compared to some other solution. So the ordered connection can be used for backward compatibility with IB verb-based application, which requires strict ordering of RDMA message completion. But the new application is designed for machine learning or some other, for example, NVMe, which is a block interface, can make use of this new, more efficient model, which is an unordered connection. So the unordered connection avoided the rewarding logic in the hardware itself, so it can provide lower latency, lower jitters for this kind of advanced applications. So Intel will do the upstreaming in the kernel to expose this unordered connection to the host application as well. So this is something coming very soon. Basically, what that means is we have to enhance IB verb and OFI provider extensions or just the new APIs to expose some new attributes like out-of-order completion, completing error handling to the application. So it can make best use of this out-of-order, unordered connections. Falcon as a transport is an open technology. Thomas mentioned earlier, Google already published this in OCP. So we have a link here to this GitHub, which includes 3 specifications. One is the base protocol specification, and then one document for RDMA over Falcon, and another one is NVMe over Falcon. So we highly recommend to download the 3 documents, look for next level design details. This is a very well designed protocol. Is proven by a top CSP. So there are a lot of interesting technologies inside this transport design stuff. So that's a quick go ahead.
I like the term lossy fabrics. Yeah. Is there a way to characterize how much of a problem this is? Is it across the board? Is it half the folks you're talking with?
One is, I think, the scalability, right? So this protocol is designed for data center scale. So it's a really large cloud, right? It's proven in a very big CSP's cloud environments. So we're not talking about like 1K, 2K nodes. It's much more than that. It's a much bigger scalability.
And it's a little bit of a catchy term, but it's because most Ethernet guys you talk to is like they say lossless or lossy, and what they really mean with it is losses. You just have to lossy. You just have to retransmit, right? It's just normally what you do, right? The TCP controls. I would say, hey, I didn't get it. I didn't remember ACK. I need to retransmit. Right. And so this is when people say lossy fabrics, which is fine. It works how Ethernet works, right? And for non-latency sensitive, jitter sensitive, or ML workloads, no issue, right? So the whole argument goes, hey, if you have an upper layer protocol application, RDMA in this case, that doesn't deal with that well, then you need to you have 2 choices, right? You either make the network lossless. This is the RDMA, sorry, that's the PFC discussion, right? Rocky PFC discussion. That's one way to deal with it, right? You just basically manage your oversubscription and put back pressure and say, hey, I see I'm starting to drop, slow down, right? That's one way of making network lossless. The other one is just, hey, I do still do retransmission, but much smarter than TCP does, right? I basically do selective retransmit. I start throttling on the endpoints without involving the network. And so that's why when we say lossy, we mean you don't do this in the network, you do it at the endpoint, right? And so that's why when you need to listen to losses is typically meant I tweak my network to make it lossless, which is really not what you really want to do because that's pretty expensive, right? In an ideal world is you keep the network running as it is, and for the select traffic that you really care about, you use the endpoints to take care of that. Both are valid options. So I'm not, it's just, does it help? Why we call it lossy?
That's helpful, yes.
Okay.
Thank you. Thanks.
No worries.
I have a question as well. Actually, two questions again. Sorry. This is Remington. So, first of all, I love that you're pushing all of this effort into the IPU, right? And that you can run a standard Ethernet network in order to connect, right? That makes it much easier.
Yeah.
We also potentially don't have to worry about PFC stalling the whole network due to the back pressure problem. So that's awesome. Great. My first question is around how does Falcon enablement on the IPU get troubleshot or have any awareness of a problem that's happening upstream in Ethernet that you might need to correct or change or do something different in order to support Falcon? Because the network now is completely dumb, has no idea Falcon's running on top of it. But I can also understand that the lossy fabric could be causing you a problem. So, like, is there any form of feedback loop around, hey, you do have a problem, we are dropping packets, you need to go do something, rather than just correcting it in the background? Does my question make sense?
Yeah, so I will try to answer the terms as usual can help. So, first, one of the beauty of this protocol is, like I said, it really does not need any special configuration in switch, right? So it works well and it can coexist with some other traffic. For example, you have a lot of TCP running, right? So if you want to enforce some isolation, one thing you can do is just minimal configuration in the switch, have like, for example, 2 traffic classes. So one for Falcon reliable transport and then one for other traffic. So you can make sure they don't have any grab each other's bandwidth, right? That's one kind of a potential configuration you can do in networking to make sure there's no starvation or no, right? But we actually did a lot of tests, and the Google team also did a lot of investigating, which is very interesting. So it's actually, when you have a mixed traffic running on the same fabric, no matter what you do in other traffic type, it doesn't hurt Falcon. And the Falcon actually helps because they already have very good congestion algorithm. So it runs better on the fabric. It actually reduces pressure on some other types of traffic running in the same fabric. I mean, doesn't that make sense? So basically that's, but from the other, how you do the diagnostic, how you do the runtime loop, we are working on that. So basically we provide the telemetry information, which is a good point. This architecture is a co-engineer with basically Google Cloud team, right? I mean, they are more a software company. So we build in very good telemetry architecture. You can see details per connection telemetry information. See a lot of details about congestion control states. So we have plenty information available to be exposed to the networking administrator. So that information can help to basically see very fine granularity of traffic, like a per connection level. And then you can change the congestion control algorithm at a runtime or just tweak the parameters, right? In case you say something which may not be the perfect situation. So in general, the architecture is built for that kind of flexibility and is easy to run and easy to diagnose, and it's also have feed loop available based on telemetry APIs we have. Make sense?
Yes, it does.
Right.
And it leads to my second question around, so there's also the Ultra Ethernet Consortium, which is, doesn't have anything other than a white paper out right now, right?
Yeah.
Do you see Falcon getting established and being a way to move forward in terms of getting off of InfiniBand or not using InfiniBand in a lot of these cases, even though there isn't an Ultra Ethernet capability yet? Like, can we just move to Falcon essentially and not have to worry about Ultra Ethernet from Intel's view, or? Yes, and?
Good question. You want to okay. So first, right? So one thing I mentioned earlier here, from a usage point of view, this transport can be used for the AI machine learning, which is in the GPU. If you talk about scale out network, right? This is a one transport. You can use that for GPU scale, basically cross 2 servers talking to each other, right? It's already used in our leading customer. So this is the one proven technology for that use case. But for UEC, it's also interesting in a way that it's highly optimized for HPC and AI and a standard-based solution. So over time, I think there will be more basic adoption and embracement of that transport, right? But here we are the one basically moving much faster. I mean, this one is available in the product shipping today. is used by a leading CSP and is open technology. We believe that some other vendors will do this as well. So it will stay there, right, for a foreseeable future.
And it would even run over UPC, is what I'm taking.
Right. Thomas, do you want to add?
Man.
Good question.
One follow-up question about Falcon, and forgive my lack of knowledge about the Falcon as a reliable transport. Is there some controller or back-end communication between the Falcon nodes so they know when to back off? So that, as Remington said, they're not all just pushing traffic into the infrastructure at the same time. How that makes it lossless? I'm trying to figure out how they know the upstream Ethernet network is getting congested. Slow down a little bit.
Yeah, so maybe we can get into that congestion control. So that's basically the congestion control algorithm was solved. But from transport design point of view, one thing I want to mention is it includes the selected ACK, right? The selected ACK and the sliding windows will really help make that packet loss recovery more efficient. You basically, if you lose one packet, you just need to retransmit one packet instead of a standard Locky V2, which use a very simple go back in, right? So that Locky V2 standard solution is not efficient. But here, from a transport design point of view, this problem is very well solved using selected ACK. And then the congestion control algorithm, which is the one I'm trying to get into here, we can talk in more details, right? This is basically provide the best algorithm to basically do the flow control and avoid the congestion issues in the fabric. Okay, so just a little bit of background before we talk about this. So all the leading CSPs often have their own congestion control algorithm, right? Because they have their own networking topology, their own workloads applications. So it's critical to have this flexibility in the architecture to enable that continuous changes of congestion control algorithm and enable that innovation. So as part of this Falcon architecture design, so we basically provide this full programmability to enable congestion control innovations. This picture is a very simple picture trying to illustrate that concept. We basically separate the congestion control from the packet delivery layer. So the packet delivery layer, right, which is the data path, I mean, doing the really processing of every packet at a line rate. So it can look at the packets and extract the interesting information for CC algorithm. So in this picture, it includes a few examples. For example, all the interesting information, ACK, NAC, retransmit type, the time steps from NIC, and the remote NIC's resource utilization information as well, and some maybe like error handling like a NAC and the number of ACK. So all this information are super useful for the CC algorithm. So it's the packet delivery layer basically sends this event information to a mailbox queue, and then the software update engine, right, will process the CC events. So one of the key decisions is to keep this software update engine running on the IP core. So in the earlier picture, we showed the ARM N1 cores, right? That's the basically server class CPU core. So this design provides full flexibility because the algorithm runs on a CPU core. So you can change the algorithm anytime you want. You can update the algorithm at real time without tearing down your system or change your whole networking path. So this is one of the flexibility very important. So the algorithm in Intel's solution, we basically build this Swift-based algorithm and add a multipath load balancing algorithm as well. So it calculates the new congestion control window, the fabric window, NIC window. In the congestion case, it can actually do the packet pacing as well using timing wheel. Like if the congestion window is smaller than 1, it means you probably need to wait for a couple RTT or longer before you send another packet, right? Which helps avoid the incast issue, avoid the packet drop. So this packet pacing capability is also critical in this CC algorithm. And then you can also control retransmit timeout. And in the multipath load balancing case, you can select which path you should go for this packet. So there's a full flexibility is built into this architecture. Again, the algorithm runs on the CPU core, so you can change it, update, and we provide this algorithm, and the CSPs can customize it or even write their own algorithm if they prefer to do. I mean, so it makes sense. So this is basically one of the very critical design decision enable this flexibility, and you can always build the best optimal congestion control algorithm for a specific application or deployment environments, so it can minimize or avoid packet drop in different fabric environments. Right.
Hi, I'm Micheline Murphy. I think it's really cool that it's open source. The Achilles heel of open source anything is, well, I've written myself into a problem that I can't get out now. How do I reach out and get a lifeline or call a friend, or what sort of support human-wise do you have for your open source product?
So it depends on the community. So basically, IPU has a lot of software components. For example, some kernel drivers, it goes to Linux kernel. It's just go through the standard Linux kernel supporting kind of practice. But we do have a lot of SDKs in user space, which we release part of this IPU SDK. So Intel will have team support for any bugs or issues reported for the open source IPU SDK. And then some other more like community like OPI, right, and SPDK or DPDK, it goes through the standard like open source community and support model. So that's the model we have.
Okay.
Okay, so that's a good discussion leading to this software conversation. So we have a lot of busy information here, but I'm going to simplify this conversation. So this picture trying to show the driver stack with Falcon enabled in IPU. So it shows from the hardware to kernel drivers to user space RDMA providers, and then on top of OFI provider, you can build all the interesting middleware like NICO for collective communications, and then the AI solution stack, right? So what I want to say here is the integration with the Falcon is very clean, because we just need a new software component for Falcon connection setup. So that software component runs inside the IPU. So it's basically use CPU core from the IPU to do that connection management and the connection setup, including telemetry and some other diagnostic capability, right? It's pretty much transparent to host the RDMA drivers and all the user space software stack. So that's the beauty of this transport. You can bring in your own OFI provider if you have something highly optimized for your application. But Intel basically offered this PSM3 OFI provider. This is the OFI provider, includes optimizations for HPC machine learning AI workloads. So it improves the performance and the scalability. And it also includes some optimizations to make the best use of this Falcon transport as well. So that's basically a short description. Okay.
So this is Ed. Quick question. So you had the CUDA side. Is CUDA actually aware of Falcon being enabled in the IPU stack? It's just transparent to it, right?
Yeah, because the only place is OFI provider. It includes optimization. So it depends on the transport. For example, it can use decide the number of connections to use to reduce the basically the pressure on the scalability. Right. Okay. So, but in general, it's fully transparent to host. So that's one of the beauty of this transport. In some other vendor solution, you might see they have a new middleware, new library. So you have to change everything to make a user. But for this one, it runs under standard RDMA IB verb interface. So you can use your own software without any changes.
So can you map particular library stacks? Like you could map CUDA to just say use Falcon versus everything else being on the IPU NIC side? Or do you?
We make it transparent. The only thing is the highest level which you might need to know is the OFI provider, which sits on the NICO layer.
Okay. All right.
Okay. So we have this software suite, which basically integrates all the key components here, and we do thorough validation, make it easy to use. So we call this as Intel Ethernet Fabric Suite. It comes with some deployment verification tools, diagnostics tools. So Intel Ethernet Fabric Suite is the one which packages everything, make it easy to use this technology. Right. We'll show a couple of data sets because the time is limited. So this is a highly simplified view. But on the bottom left corner, is a simple chart to show this transport works as designed for. It delivers very stable, good throughput under heavy packet loss compared to Locky V2, all right, which is standard solution. So look at the Locky V2 here. Under, for example, 2.2% packet drop. I mean, by the way, this test is very simple. We basically control the switch, right, to do the random packet drop. If the 0.2% drop, you can see notable throughput drop from Locky V2. At a 0.5% drop, it's reduced to half. And if it's in the extreme case, like a 1% packet drop, Locky V2 pretty much is not usable. The reason, again, is because the go back and retransmit, right? Which basically for every packet drop, it just retransmit too many packets. So it really hurts that good throughput. On the other hand, Falcon solved this problem very well. I mean, because we use a select egg, sliding window, and all the interesting techniques we build into to reduce latency jitters. It's retransmit only the packet drops. So if you drop one packet, I retransmit one packet, right? So overall, the throughput is very stable. Like even at a 1% packet drop rate, it's pretty much stay close to 200 gig line rate. So this is a proven number from real silicon. It shows that it works as it's designed for. The second data set, which is on the right bottom corner, trying to show the latency test. So this is for RDMA write test with different message size from a 1 byte test to 2 megabytes test. The chart is a little bit busy, but it's intended to be that way. So it includes quite a few data points, right? The minimal latency, median, average, 99 percentile tail latency, and the theoretical number in green line. If you look at the chart, you cannot tell any difference, which is the beauty of this transport, right? It basically means the jitters are super low. Like even at a 99% tail latency, it's close to the average number. This is a very critical attribute of this transport. It just helps a lot and improve performance for all the interesting distributed applications, distributed microservices, right, in large cluster. And the same for the machine learning and AI. I mean, it's very sensitive to jitter. So, so this transport will improve all the new workloads for HPC, machine learning, AI. Right. So we call this as a predictable performance. So this is one very important aspect of this transport. It can really shows the value, right, from the application performance point of view. So as a quick summary, this is Falcon reliable transport meets the need of the day. It can meet the requirements for all the critical workloads, including HPC, machine learning, AI, and all the traditional RPC and the storage networking. It delivers predictable performance as the data shows here. In data center scale, right, is a really large cluster. I mean, it's not like a small cluster. It's a true data center scale networking. It can fully benefit this transport to show that a very low tail latency, and that the applications can deliver full line rate. It comes with all the state-of-the-art new congestion control algorithms. Because it's a hardware transport, it can really deliver efficiency at a scale. It delivers this line rate bandwidth, very low latency, right? No matter how many connections you have. I mean, some other solution might say, oh, if you go above 1K RDMA QPs, you will see a lot of performance degradation. But with this transport, it can go to very high. I mean, we designed this for 1 million connections. So it scales very well, I mean, with the number of connections. So that's basically the quick intro of this transport. I think we have a few minutes. We may be able to take a few more questions. Go ahead.
So I've got a question for you. And I guess as I look at this all makes sense to me. I'm just trying to like practically put this into a network. You know, like where are we going to see this? This to me, and correct me if I'm wrong, I guess it's part of a statement, part of a question. This is really going to be geared towards, just like on the IPU, towards OEMs who are writing capabilities who need reliable transport. As an engineer myself, if I'm deploying something, I'm not necessarily going to deploy this directly unless I have a very specialized use case. Instead, it's going to be a storage OEM, or it's going to be a hypervisor, or it's going to be something like that. That's really going to dive into this. I'm trying to figure out is there something that like me as an architect or as an engineer on an enterprise network is going to interact with this directly, Or is this something that the software that I consume is going to use this to optimize traffic?
Yeah, I had a feeling.
Yeah.
So what I described earlier, I think the way this is going to work out, you say, hey, for these servers, I need this capability.
Yeah.
I populate those servers with an IP NIC.
Yeah.
And then you use the software stack you see there to manage and turn on. And I think there was an earlier question. Yes, we will work out a lot of interesting discussions like network controllers. How can you connect what we have to configure and monitor was in the Ethernet Fabric Suite, which is, by the way, open source too. How can you connect? There's clearly value from an operation perspective. I think there was a question earlier. But yeah, I mean, the way I envision this is you're going to deploy your network as is. That's the beauty of it. If you say, hey, I need these 10 racks or these 20 servers, whatever the number is, right? I need that capability. I put these NICs in there, and you turn it on there, and don't touch anything else, right?
Because
I'm sorry.
well, no,
Yeah.
I mean, it seems like the advantage is that
Yeah.
you're picking stuff on a per server platform basis.
Yeah.
Yeah.
As long as you as an engineer understand what you're buying,
Rather than
From a
building it
capability.
into the network fabric.
as opposed to building.
Right. And I understand the need for reliable transport over
Yeah.
Ethernet. Like I understand where this is going and
Yeah,
why
yeah.
it's needed. I guess I'm just trying to figure out like we're in this influx time of where new stuff is coming to the market. I'm trying to figure out like where as an engineer architect do I need to be paying attention to this stuff?
Yeah.
Or is it OEMs right now who are primarily paying attention to this and that it's going to start to involve itself in my networks? I'm just trying to figure out, and also there's obviously different types of networks. Obviously, inside of Google, they're using this heavily. I get it. You know, like, because they
Like,
have
how do we get to a winner?
a very specific need. Yeah, like I'm just trying to figure out, like,
Well, I'm
you
not.
said at a Fortune 100 enterprise, like, what are you supposed to be paying attention to with Falcon right now, or is it the OEMs that are
Like,
primarily?
so here's, and this is a little bit me coming out of the enterprise networking
Yeah.
world, right? The way I would think about it, right, based on my background, and I'm not saying that's customers do it necessarily, but
Yeah.
the way I think is you build your network today, right? Today, what you do in a typical enterprise, you just an Ethernet network, right? You do all the magic you need to do, and then if you have hosts that basically need what we call GPU connectivity, right? To scale out, where you do really need over the network reliable transport capability, losslessness, right? You have two choices today. Either you turn on for this ports PFC and Rocky, right, which is basically the only choice that existed, or you have going forward a choice saying, hey, you know, instead of doing that, I just plug in these host IP NICs and turn on Falcon, right? These are the two choices you have, and it's really more a decision in how do you want to deal with that requirements for reliable transport for a certain set of application, right? Because the assumption in the enterprise, at least I have, is you're not building what people call AI factories, where you have a network dedicated just for GPUs. I said that before I joined Intel, and I still say that. I don't think that's going to happen, right? I think you're going to have a joint Ethernet network, shared Ethernet networks, where maybe in a large enterprise, maybe you have 20% of your hosts being GPU based. That I think is going to be a high number, but even with that, you're going to have a shared network, right? And so what you want is that ability to turn on reliable transport where you need it, instead of making it a problem for every host. And that's the beauty of this approach, right? Because you basically don't have to touch everything else.
And that operational group then incurs the cost.
Correct.
So they can pick up your Intel
Correct.
IPU, pay the
Correct.
price point for their platform to take care of that cost center,
Yeah.
and they don't have to put it into the network, which is going to be exponentially higher cost.
For reliable transport, they don't have to. It's
Right.
not that exponential, but
Come on, it's exponential.
it's just calling out an hour.
Do I need to teach you how to sell now, Thomas?
Okay.
No, that makes sense.
I had a question. So Falcon, and we were talking about, I keep coming back to the capabilities of the IPU, right? Just trying to differentiate it out. So this is a transport capability that doesn't presumably impact my ability to either A, run throughput through the card, or B, run any of those functions on the ARM course, right? So I just say I want to use Falcon, right?
Yeah.
Well, I can do that, and I can do it at the normal line rate I would if I ran it not Falcon, and I can do all the other functions I want on ARM, Falcon or not Falcon, however I want to run.
With one minor caveat, if you paid attention to the congestion control,
Uh-huh.
2 of the 16 cores are gone because you
Okay.
need to run the congestion control algorithm there, but you have the other 14.
I gotcha. Okay.
That's to be very precise, right?
Okay.
We need
Appreciate,
just one.
I appreciate
actually.
your
W-
precision.
One or two.
Just
one
one.
or two. See, he
Maybe
says
one for
I
OS.
say 2. So the majority is still available.
Right.
I got that. Okay. So so
So
that's basically.
do you
the
see, So do you see other use cases where you're using Falcon with the IPU, like in low latency trading environments or in low latency media streaming? I'm trying to think of other use cases outside of just storage infrastructure.
Yeah, so for storage, yes, perfect use case because earlier we mentioned that this NVMe over Falcon hardware path, right? So that's one very low latency, high throughput storage flow for the block device level and kind of applications, right? But you can also always run your storage application if you use IB verbs like over RDMA. So the RDMA over Falcon path is also available. So so it's a that's one of the reasons we support this IB verbs backward capability. So all the storage application today runs on top of IB verbs, can make use of this transport right away.
Yeah. And I think the other question you had is, are there other application? I'm very sure if you look at some of these cloud providers, what they're trying to run, some of these you mentioned, I think is clearly on the radar. So yes, I do think there's a lot of opportunity. I would lie if you say we haven't figured it all out. There are 2 or 3 very obvious ones, the ones we talked about, but clearly that protocol enables a lot of other things where you just have a better application experience because you have a smoothed out read transmit selective instead of the lossy way.